Okay, so let's kind of catch ourselves up on our procedure. So right now, we did our torques, we determined our forces. In our case, we're only worrying about the gears. We need to determine the directions of those. So we determined the directions, but now we've got to take it the next step further. We're going to turn the page here. And now we're going to, because this would be determine the directions on a sprocket, determine the directions on a sheave. These are not applicable for us on this example. But number 8 is draw and sketch the free body diagram of the shaft using all the forces and bearing reactions. Okay, so what we are going for here is at the top of page 523, we're going to generate these two orientations. I'm not even real crazy about the way that they did this because the right hand side is a front view and the left hand side, they did a bottom. We're going to do a top. That's like normal. And then their 12-2 is a top down. So we're going to see the same numbers come up here, but we're going to notice our directions are going to be exactly opposite just because we're looking straight down as opposed to looking up. Okay. And then from that, we'll use MD solids to generate this. So what I want you to do on a piece of paper, getting out a straight edge, you are going to create what you see here. All right. So I'm going to move the control in the room. I've done this before. I think it's easier if we kind of make this a little bit darker. But those who are online, what we're going to do is we are going to create 3 views of this shaft. And we're just really going to show the center line of the shaft, if you would, really not as a center line, just as a line. So this is going to be my front. This is going to be my top. And this is going to be my right side. So you'll notice that what I just use a straight edge, okay, just like this. And I just created a random length. And I started on the left-hand side with A, B, C, and D. And then you'll notice that I've got room for a right side view. Okay. So I'm going to give you a chance to create this right now. All right. On a piece of paper. This is going to be part of what you hand in for your practice problem and for any parts of the assignment, even though you're going to be then duplicating this in your MD solids. This ensures that you understand the directions of these forces. Going through this process is really important. It's taking that 3D mind, putting it in a 2D orthographic projection. So this is going to be our top view. This is going to be our front view. And this is going to be our right side view. Okay. Now, this is not sketch in the sense of, you're just going to, freehand pencil it. Straight edges. You must use straight edges. You have to be neat about this. I'm going to be a little bit of a stickler on this. You guys are in your final semester, second to last term of your second year here. I want you to be presenting things in a way that's readable and professional. You're not chicken scratching your way through life anymore. I would be. I'd be like, you gotta be able to read them. You want to give a good impression. The neater it is, the more confident somebody's going to know you did the right thing too, believe it or not. And again, I mean, you don't have to worry about the distances being perfect. It's a representation left to right, but nice straight. Identify the points, our critical sections, A, B, C, and D, and then write a room for the right side view. This is probably, well, I'm not going to say it's the most critical, but it kind of is a big deal. Directions of the forces are really important because they dictate our shear and moment diagram. Okay. So this part is actually really important to take your time and make sure we've got a good handle on the directions here. Now, as we look at our sketch, okay, the two places we are not going to be calculating anything for right now, and we're not going to actually do any manual calculations, we are not going to worry about any forces at B or D. We just need to know they're there, right? Because these are our bearing reactions. And as I said earlier, MD solids is going to help us with that. They're going to actually, MD solids is actually going to calculate that. I'm also going to add in here my lengths. This is 10 inches between A and B. It's 15 inches between B and C. And then it's another 10 inches between C and D. Okay, so that's just to kind of let us know where we're at. Again, you don't have to add all the arrowheads and all that kind of stuff. It just adds to, but we're going to be needing that locational information from center to center for our MD solids. Okay. So as we're looking here, so what we're doing, again, I'm going up to the top of page 522. Okay. And my front view, starting left to right, is our A, B, C, and D. So I'm looking straight on front view there in this view right here, this bottom one, the straight one. Okay. A is on the left. Our y-axis is going vertical. Our x-axis is horizontal. And our Z is a point in and out of the screen, right? Okay, that's why I have the Z there. Then the other view that we have is going to look straight down on top, where we're going to see then Y as a point. X is going to still be horizontal, but our Z is going to come out in the front here. So as we look at this view, X is still in this orientation. Y is now a point because I'm looking straight down it. And our Z, our positive Z, is coming forward. Okay, that's that standard 3 axes. And then our right side view, they do not do a right side view. I'm going to do one with you because I think it's going to help, I think, make it easier to visualize. So my right side view is going to be in line here with my front view. And then my Y is going to be vertical. My Z is going to come to the left, positive Z, and I'm looking down my X axis. So my right side view is going to be this orientation, okay? And I want that one because I want to see my gears as circles so I can show exactly where this is going on, okay? And then I'm going to translate that into the front and the top views, which we will use then for MD solids, okay? So good. All right, does everybody have kind of that perspective? Everybody got these in place? Anybody need a little more time? All right. All right, so if not, then we're going to start with our right side view. So like I said, I'm gonna start with point A first, all right, just because it's over here. And I am going to represent A with a pretty large circle here. This is going to be in the right side view. When I look down my shaft, this is going to be A, as I see it as a gear, okay, in its circular view. Now I know you probably don't have a circle template. That's okay. Just kind of do your best with that. It was back in the, well, a long time ago. I won't say what years. We got to use these. It was so fun. So fun. Okay. And now as I look at this orientation, I look down the x-axis and I'm looking at A right here. Notice that to the left, right? To the left, I would have gear P. That's going to be my coming in. So on the left here, I'm going to draw this little gear P. Okay. So this is gear A. Okay. And this is P. Okay. P is not on my shaft. I only need it for the orientation of where I have engagement. Okay. So when I look at P and A, they come together right here, right? That's their point of engagement and that orientation. Now, my radial force is going to go from the point of engagement and it's going to point towards the center of rotation, right? So my WRA, the radial force at A, is going to point to the right towards its center of rotation. Because the shaft is right here, right? The shaft is right there. Now, The direction of rotation is counterclockwise. I'm just going to draw it like this, counterclockwise, just an arrow like that. So now remember, A was driven, right? So I'm going to put driven because P is driving it. So since it's driven, my tangential force is going to be perpendicular to the radial. It's going to point down. This is going to be my WT at A, and it's going to go in the direction of rotation, right? It's a driven. Any questions about that? Pretty easy. All right. Now, let's translate those into these two views. So let's do our tangential. Our tangential is vertical right here. So it's parallel to the y-axis. When I take this and I put it up on its end and I look down, do you see how my tangential is going to be pointing down on A? Right? Agreed? You see how that's going to go from here to here? Now, this is where we have to look. And I use my thumb. So I know that the radial is going to be I should go this way. It's going to be to the left or to the right here on my right-hand view. So when I look straight down on it, do you see how when I look in the top view, it's going to be pointing backwards? Do you guys see that? If I go here, you can see that it's pointing back. So when I go down and I look down on it, it's going to be pointing this way, right? From the top view, not the bottom. We're doing top view. So now that means that I'm gonna show it on the top here just because it's easier. Whether you show it on the bottom or the top does not make a difference. My radial at A because of, it's the statics. Whether you put this going up from the bottom or up and pointing on the top doesn't matter because of the principle of transmissibility. You guys remember that? I can move it anywhere along its line of action. It's gonna have the same net effect on the body. Just talking about that in statics, actually. Now let's put the magnitudes right away. And we remember our magnitudes from our Excel spreadsheet. So we're going to go down here to gear A, and the tangential was 764.31. And that's pounds. And our radial, I'm so sorry, I read the wrong one. Radial is 764.31 pounds. And our tangential is 2,100 pounds. So direction comes from the orientation here. Magnitude comes from our spreadsheet. Okay. And we'll use these values when we go over to MD solids. Okay. Now let's put gear C on here. Gear C is smaller. So when we look here, gear C, remember, is the driver for gear Q. So I'm going to put a smaller gear at the center here. Okay. We'll make it about, gear C will be here on the same center. Okay. But it's going out to a larger gear, and this would be gear Q on the back side, opposite of P, right? So this is gear Q, and this is gear C. Now, gear C, as we said earlier, is the driver. It's a driver, okay? Now, its radial force is going to act the very same way that a driven did, that A did. So we're going to find the point of contact, right? Right here, or point of engagement. And our radial force, WRC, is going to point towards the center of rotation. So it's going to point to the left in this view. Do you see that? Radial is always going to go from the point of engagement and point to the center of rotation of the gear that we're analyzing. So WRC. Tangential. We're going in a counterclockwise direction. Our tangential is going to be perpendicular to that radial, but it's now going to be opposite the direction of rotation. So if we're rotating this way, our tangential is going to up or down? Down, right? Opposite the direction. So this by WTC is down. So WTC, my tangential is parallel to my y-axis. So over in my front view, it is going to go down. Let's see, WTC, and we'll get that magnitude in a little bit. Direction of C. When I look straight down on this, do you see, and you can even, you can kind of look here, might be easier. Look straight down. This is going to be pointing down in the top view, the radial force, okay? And it makes sense because it's opposite what A was. So this one's going to be pointing down. WRC. That makes sense to everybody? Any questions on that? Going from right side view to the front view to the top view. Now we just have to add our magnitudes from our spreadsheet. So this is going to be C, these two right here. So my tangential is 4,200. And my radial is 1528.63. And both are pounds. Okay. Now, this is what you will hand in to me. This is as far as you have to go with this part of it. I need you to have your gear forces in the orientations with their magnitudes. I want to see front, top, and a right side view. All right, so we can see exactly where those forces are. You don't need to determine the reaction at the supports because we're going to, MD solids is going to help us with that. Okay. If you wanted to, for old time's sake in statics, I mean, I get it. It's fun. And which one? This is tangential and this one's radial. Yep. Sorry. I know it's not that easy to read up here. So tangential is in the front view for both of these. That's not always the case. I'm going to tell you that. These just happen to work this way out. And then up on top are radials for both. Yeah. Mm-hmm. Yep. Well, and the other thing is too, tangentials can change. What if my engagement's down here? Then that orientation changes as well. So don't think that the radials are going to be on the same shaft or in the same orientation and the tangentials will be. They may not be all the time. All right. Everybody here, do you feel good about this? Hopefully that was helpful just to kind of get that visualization. So now what we're going to notice, let's look at their free body diagram. And I'm just looking at this part. Their front view matches ours, okay? But their bottom view is not a top view. And I just don't see the point in doing a bottom view. That's just like not normal. But you'll notice that their directions are exactly opposite of what we had. And all we're interested in the shear and moment diagrams is not so much the direction of it, it's the magnitudes that are generated. Okay. So we'll notice that it's just opposite. It's not a big deal. Okay, so now we're going to take this and we're going to put this in MD solids so that we can calculate for us the reaction of the supports and generate our shear and moment diagrams. Okay, shear and moment diagrams. So we're going to open up MD solids. So wherever you're at, I have mine on my desktop. You probably do too. You're going to open up MD solids. Now, if when you open it up, it's asking you for a registration code, you've got to go back to that download file, that download page, and there's like a DC, blah, 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 blah. You're going to input that. And then you're also just going to give it a username, like an initials or something like that is fine. And you're going to come up to this menu. Okay. We're going to click on determinant beams, right? And in the upper left-hand corner here, you're going to notice that we have a selection of different types of beams. The one on the upper left-hand corner there is going to be a simply supported beam. Now, yes, this is a beam, and you're like, but we're working with shafts. We're simulating the shaft like a beam, and the bearing supports that we have are considered simple supports, okay? So we're gonna click on that one, left click on it. And now you're gonna notice that it's gonna ask you for some information about the beam or the shaft. Now, in our case, the total length of the shaft is 35 inches. There's 10, 15, and 10, right? So, I mean, between centers. So 35, and make sure that your units are the appropriate units. So make sure that that's inches. And then it's going to ask, what is the location of the supports? This is where our bearings are. Bearing B is 10 inches in from the left. So we're going to put 10. And then the location of the right support is going to be 35. Okay. And then you're just going to hit enter or okay. Now you'll notice on the right-hand side, I'm going to move this away for a little bit down here. On the right-hand side, this is simulating the length of our beam. You'll notice that it has some dimensions here. The thing that we can't change is they are calling the first support A and the second support B. That's actually our B and D. All right, we're just going to have to know that. That's all. Not a big deal. Now, over on the left-hand side here, you're going to notice that we have the ability to put different types of elements. And we are going to now go back underneath here. Oh, come on, move out of the way. Zoom, there we go. And now what we're going to do is we need to draw, I'm going to start with my front orientation. So I'm going to draw a downward arrow. I'm going to select a downward arrow, and its magnitude is going to be 2,100 pounds. Okay. So going back to MD solids, downward arrow first, and then it's going to say, okay, where's the location? We want that right at, notice the 0 location here in the diagram is where A is. That's where we're starting everything. So that's going to be at 0 inches. Its magnitude, it's going down. So make sure that you pick the right one here. Okay. And it's going to be 2,100, and make sure it says pounds. And then you're going to hit enter, and it's going to put it in place. Then we're going to scooch over, and we're going to now place another one going down to represent WTC. And that is going to be at a location of 25 inches. And its magnitude going down is 4,200. Okay. Now, do you notice something? Directly below is our shear diagram. And then directly below that is the moment diagram. See that? Okay. Automatically does it for us. The reactions of the supports, if we just arrow down here, we see those reactions at the supports. Okay. Now, we need to get a copy of this. All right. Many times we would probably print it off, or you could save it, but we're going to have to go back to it. So what I suggest that you do is you open up some sort of document. I always default to Microsoft Word. Okay. And we're going to grab the screenshot then of the MD solids. Now on my laptop, and I think on most laptops, it's going to be Windows Shift S. And then we're going to just click, drag, 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 and make sure you get the whole thing. And then you're going to go over to Word. And this is example 12-1. And this is going to be the front view shear moment diagrams. Okay. That's all that I just want to call it something. And then I'm just going to do Control V to paste that in place so that I have it. Okay. You could save this. You could print it out. All right. But we can just have it available here because we're going to be referencing this. And then what I suggest that you do is you file, save as this document somewhere. Okay. I'm going to browse to, again, my desktop. I kind of default there in a pinch desktop. And this is just going to be example 12. I'm going to go _1 and then shear moment diagrams. And then that way I have it saved because I'm going to need to attach this to your assignment when you hand this in, okay? All right, any questions so far, MD Solids? It's amazing, right? Think about how long it would have taken. I don't know, you guys, depending on how you did them, but this is such a really nice, it's such a great tool, and especially graphically, it gives us the information that we need. Okay, so now what we're gonna do is we're gonna go back underneath, and we created this one, all right? Now we're gonna go and we're gonna create the top one. We need to create two of them because these forces are 90 degrees to each other. We need to have both orientations. Otherwise, we wouldn't see, in this case, the radial forces. So now we're going to start a new one and we're going to create these. So I'm going to go back to MD Solids. And what you want to do is you want to go up. I'm going to do back on the right-hand side. And I'm going to go to File and Reset. Okay, so I did back on the right-hand side and then File, Reset. And now I've got a fresh set of beams. Okay. Then I'm going to click on this and I'm going to put my new information in. I'm going to have to re-identify the length of my beam is 35. The same placement of our bearings is 10 and 35. Enter. And now I've got a new clean beam. And now this time I've got an upward directed arrow. That's going to be at the 0 location. Magnitude is 764.31 pounds. Click enter. And then we're going to do another, this one is going to be a downward arrow at C. And this is going to be 25 location. And it's 1528.63. Enter. And now you should have your shear and moment diagrams look like this. Okay.
Hey, Kelly,
Once you have, what was that?
Can you go back through how to like refresh that?
Sure. So you're going to go back through to refresh it. You're going to go back and you're going to go over to files on this side, on the left-hand side, and you're just going to hit reset. And now it's fresh. So the loads come from here, Jesse. Did you write those down? Yep. So we're going to do the top. Yep. We're doing the top one right now. And so we're going to click on here. We have to re-put in, we refresh this. So it's like a brand new beam, 35 inches. The support location, the first one is going to be 10 inches in and 35. Enter. Now we just have like a clean beam. We're going to add our forces on the left-hand side. On A, it's going up for this first one at a location of 0. So I'm going to leave that. My load magnitude is 764.31. Hit enter. And then a downward arrow for WRC at 25 inches. And this one is 1528.63. Enter. Any questions so far? So this is our second orientation. So again, I'm going to capture the screen snip of this. I want to expand out the reactions just so we have them. I'm going to do Windows Shift S. And I'm going to start in my upper right-hand corner, then drag, 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 release. And then I'm going to go to my Windows document and I'm going to go on the next sheet. And I'm going to, what did I call it before? I think I said front view. So this is going to be top view. Shear and moment. There we go. And then I'm just going to do a Control V to paste that in place and then do a quick save. Oh, it must be saving it. I've got that on auto save on. All right. Just make sure that you've got it. That way now we've got both orientations and we will be referencing and using these numbers. Okay. So any questions right now about MD Solids? I'm going to go back over here to reset. Now let's say you're like, oh crap, I forgot how to reset. Then just go like this, X out. Oh, I gotta move this bar, hold on. X out, and it goes back to this menu. You can just start over. And now again, it's refreshed just like we would have done the refresh. Either way. Oh, you can't. Oh, then you can just go out, just go back out and then re-go into determinant beam, or you can even X out completely, go back in. I am going to tell you something about MD solids, okay? It is not the most sophisticated software. Super easy to use, super convenient. It gives us exactly what we want, but the last time this was updated, I think it says in 2013, all right? Every year when we get like a new version of Windows or anything like that, I'm always going, okay, I'm hoping it's still going to work. And it does. All right. It does. It's a solid program, but it is a little quirky on stuff like that. And if you want to make sure that you kind of get rid of everything, going back out and coming back in, it's not a big deal. Okay. All right. Any questions MD solids wise so far? Very, very easy. Determinant beams is going to be the section we want to go into. Okay. So very helpful for making those shear and moment diagrams that otherwise would take a while. So, so let's go underneath and let's take a peek at and compare our shear and moment diagrams to what they have. Okay. So what I want you to do is just kind of look at your max shears, your max moments, and just be sure that when you look at your values, that the charts look and the values are the same. They should be exactly the same. The only difference down here on the bottom one, because we did the top view second, is that they're opposite directions. And that's because they were looking from the bottom up as opposed to top down. Okay. So otherwise our numbers and everything else is exactly the same. Right? Okay. Now I don't want to move on. Does everybody, don't want to move on until everybody's got their MD solids taken care of. You've got screen snips, you've got it in a document kind of set out there that we can reference when we need to. Okay. Does anybody need me to hold on for a minute before, as you catch up? Okay. So then what I'm going to do is let's take a peek underneath our camera and look at our process. So number 8 was draw or sketch that free body diagram that we did. That was, that's this. Okay. I want to see this, that you guys did that. So we did that together. And then we inputted that sketch into MD solids to determine the shear and moment diagrams for both orientations, right? So we've got that done. Okay. So now you'll notice step number 10 is sketching a torque diagram, sketching a torque diagram. So a torque diagram, all that it's going to do, and the book has one, but I always want you guys to do it as well. It's just a representation of where the torque is coming in and where it's going out. Okay. Per our problem statement, everything is coming in on A through P, right? And then it's going to be transmitted over to C, and it's all going out at C. So all that this diagram does is it shows us pictorially the torque is coming in on A. It's going to be 21,000 until it gets to C, and then it's going to leave. And notice that it's on center, it's coming in, and it's leaving on center. All right. And that's going to become important a little bit later. So the next thing that we're going to do is we are going to generate a torque diagram. Okay. Now we're also going to create something called a conditions diagram. The book doesn't do a conditions diagram. So what I'm going to encourage you to do is put your paper so that it's like, I think this is called portrait, right? Portrait orientation. The landscape was nice to have kind of the length here for our shafts on our free body diagrams. But here we're just going to create, this is step number 10. This is going to be our torque diagram. Okay, torque diagram. Now you could do this in CAD. All of these things you could do in CAD if you wanted to. All right, but I think it's just kind of easier and faster. So all we're going to do up here, and I just want to take maybe the top third-ish of my piece of paper or a quarter. I'm just going to draw points A, B, C, and D. Okay. I know that I don't even need to know the lengths. And then all I'm going to do is I'm going to draw a rectangle coming up at A. Or a line coming up at A, same distance-ish line coming up at C. And I'm going to draw this rectangle right here. And just gonna kind of hatch this in. And this is gonna represent 21,000 pound-inches of torque coming in, and say in at A, out at C. That's it. But you need to generate it. It might not seem like a big deal, but we're gonna be referencing back to this. That's the torque diagram. Okay. So that means we can check off step number 10, right? Now, it says here, reference sheet 1 for the torques for the application. So I'm just remembering, if we go back on our Excel spreadsheet, sheet 1, the torque that's generated is 21,000 pound-inches. And it's going from A, oh, I'm sorry, I put A to A. A to C. A to C. Okay, so we've got that done. Our step number 11 is going to be draw/sketch a conditions diagram for each critical section. So this is a conditions diagram. The book does not do this. I'm going to say I invented this. This is how we're going to be able to determine what's going on in each section so we can pick the appropriate place to do our calculations for our minimum shaft diameter on sheet 2. Okay, so we've got to plan it out first. So we're simply going to draw. So this is going to be step 11, and this is going to be conditions diagram. Okay, conditions diagram. So we're going to do that very same thing. So right now on my piece of paper, I'm right about here. And in the middle, I'm going to draw my horizontal line representing the length of my shaft. Okay. Now I'm going to draw on the end here a line going up about this tall. Okay. And then a little further in to represent B, I'm going to do a line going down. Okay. Then I'm going to do another line going up to represent C. And then one last one going down to represent D. Okay. And then, so this is that center line. This is going to be A. This is going to be B, C, and D. These represent the center lines of each one of those points. Okay. And then what we're going to do is we're going to identify at the top of A here, we're going to say L and R for left and right. Then at the bottom of B, we're going to do L and R for left and right, the top of C, and at the bottom of D. So, and this is just kind of setting it up. Okay. So now what we need to do is we need to identify what are the conditions that are present at each one of these places, left and right, if there's different conditions going on. And if there is, it's appropriate to have a left and a right. Okay. So now what we're going to do is, and I printed off my shear and moment diagram. So I'm going to be looking underneath here for my shear and moment diagrams instead of flipping back and forth on the screen, but you can verify it on the screen. I have the very same thing here that we generated. So, oh, an L and an R. Yeah, it is. It's an L and an R. Yep. Left and right. Thank you. So now what we're going to do is we're going to go through those things that we just kind of created. So number 1, we're going to look in our shear and moment diagrams. We're going to identify where shear and moment is. We're going to look at our torque diagram. We're going to see where's the torque. Then we're going to look back at our arrangement that we made on how we're planning to locate and transmit the torque and the rotational speed and see what KT factors are present in each one of these locations. Okay. So first things first, we're going to look at this diagram, or no, I can do it over here. I can do it over here. I don't think you have to do that. I'm going to start with my shear moment diagram. Okay. So here's where I'm going to know if there's shear present or if there's and if there's moment present. Now, remember that all of these locations are on center to each one of these critical sections. So this is the center line of A. This is the center line of what would be B. So I'm going to call this our A because it's ours. This would be the center line of B. This would be the center line of C, and this would be the center line of D, okay? So now as we look here and we go down, this is all in projection, shear and moment diagram wise, right? So do you notice on A here that as I go down, I only have on center shear on the right, and there's really, we're going to say no moment, but there's only something starting on the right of that center line. Do you see that? Yeah. So there is nothing to the left. All right. So on point A, then it just means that we're not going to be worrying about that left side. Okay. And we can say the very same thing for point D as well. Point D's center, everything stops on center. So the right-hand side of point D, we don't have to worry about. Okay. Everything is going to be on the insides or the confines of to the right of A, left of D. Okay. So let's start with A on that right-hand side. We're going to look. Okay. I need to know, is there shear and is there moment present? So here you're going to notice that here's the center line of A. This is my shear diagram, is the top one in that printout. And I do have shear to the right-hand side of A. So I'm going to put SH at the bottom here, SH. I'm going to do the same thing for the bending moment right here. Now, here's my center line, and it's just starting to ramp up, but it's considered 0 at A. All right, so we're not going to call that anything. It's when we get like to a position like this, now we've got moment. Okay, so we're going to consider no moment there, so I'm not even going to put M there. Now we're going to look up to the torque diagram. Do I have torque on the right-hand side of A? Yes, I do. So I'm going to put a T for torque. And then what I'm going to do is I'm going to go over. So what I've done here now is I've looked at my shear, my moment, and my torque. I always do that first. Now I'm going to look at stress concentrations. So when we look underneath here, here's A, center line of A. We're only looking to the right. I've got a profile key because it goes on both sides, right? And I have a shoulder with a well-rounded radius. Okay, profile key and a well-rounded radius. So I'm going to go into my chapter where the stress concentrations were. And the stress concentrations started on page 516. And a profile key is a KT factor of 2. So you're going to put on your conditions diagram on that right-hand side, KT equal to 2. Okay, KT equal to 2. And then I'm going to go over to the well-rounded radius. This is on page 517. The well-rounded radius down here, KT factor is 1.5. It's at the bottom here, but it's also at the top of the next column. So KT is 1.5. Okay, and we're just going to leave that there. So the right-hand side of A is done. Now we're going to do the same thing and we're going to work through, but this time for B, we're going to look left and right because now we've got possibly different things going on. So first things first, I'm going to go to my shear and moment diagrams. Okay, I'm going to notice at B here, I've got shear on the left, right? And I've got moment on the left. Now, I didn't turn the page and I should have on the last one, but just because it's here, I already know that it's there. You're going to notice that it's also on the other side. It's just going to have different values. We'll worry about the values in the spreadsheet. Okay, I'm just identifying what's present here to help me know where to go in the spreadsheet. So I have shear on the left-hand side. I have shear on the right-hand side. I have moment left, moment right. So we are going to put left and right here on B, shear, shear, moment, moment. Again, not worried about values at this point. Spreadsheet, we will. Now I'm going to look up to the top here. Do I have torque on the left-hand side of B? Yep. Do I have torque on the right-hand side? Yes. So I'm going to put T, T. Now I'm going to go over to B on my diagram, and B is a bearing. B is a bearing. On the left-hand side, we turned that down, and there is a well-rounded radius there, okay? So we have a KT for a well-rounded radius on the left-hand side of B, And on the right-hand side, because we're locating a bearing, that's going to be a sharp radius or a sharp corner. So we're going to go back in here. And left-hand side was the well-rounded, 1.5 is going to be our KT factor. The right-hand side was a sharp fillet for the bearing, and that's going to be 2.5. So we're going to go back underneath here. Left-hand side, KT is equal to 1.5. Right-hand side, KT is equal to 2.5. So 1.5 left-hand side, well-rounded. Right-hand side, 2.5, sharp corner. C. Go to my shear moment diagram. Here's C, center line of C, right? Coming right down here, C. I've got shear on my left, shear on my right. I'm going to move down. I've got moment on my left, moment on my right. And again, you're going to see that very same thing, different numbers happen on the second page, but just the presence of. So I've got shear, shear, moment, moment. Now we're going to go up to our torque diagram. Here's our center line of C. Left-hand side, torque. It goes out on center, no torque on the right-hand side. You guys see that? Okay. So we're going to go down here. Torque on the left-hand side. I'm going to leave torque off. I'm not even going to put a T there at all. Nothing for torque on the right-hand side. Now I'm going to go back to my diagram and see how I have this set up. So at C, center line, left-hand side first. I'm locating the gear on the left-hand side. I know that as a designer, I have control over that radius. That's going to be a well-rounded radius. So my first KT factor is going to be 1.5. You'll get to know these soon. All right, 1.5. So my first one is 1.5 on the left-hand side. 1.5. 1.5. That was the well-rounded radius. What other stress concentration do I have on the left-hand side? The key. What type of a key? Is it a profile or a sled runner? The profile. So my profile KT factor is 2. So I'm going to put KT of 2.
Now, is that considered on just the left?
Yep.
No, it's-
Yep. Well, we didn't go to the right yet. Yep. All right. Now we're going to look on the right-hand side. We already said there wasn't any torque, but there's moment and shear. So now we're going to go back over there. We're going to look on the right-hand side and we're going to see what's going on. So like BJ already alluded to, yeah, that keyway extends on the left-hand side and the right-hand side. So we're going to put profile key KT factor of 2.5 on the right-hand side. Oh, 2, sorry, yep. 2. Ooh, 2 for, yeah, 2.5 for the other. Yeah, thank you. And then on the right-hand side, what else do we have? A retaining ring groove, right? Retaining ring grooves. So retaining ring grooves, they don't show us a picture of retaining ring, but on page 517, KT factor is going to be 3. KT factor is going to be 3. All right. Now, if there would be more KT factors, we continue to list more if there were. All right, D. Go ahead and do D by yourself. See what you come up with. Now, remember, it's only the left-hand side for D because everything, ends on center. See what you come up with for D. On page 512. It's at the beginning of the chapter. Okay, so as we look at D to the left-hand side, we're gonna look first at our shear and moment diagrams. D is on our very right-hand side here. There is shear on the left, right? There is no moment on the left. Yes, it's kind of coming down, but it's considered zero moment, okay, on the left-hand side. So there's just gonna be shear there. And then if I go up to the top here, my torque and left on C, so there's no torque here. And then now I'm gonna go to the left-hand side. And I've got the bearing there, and on the left-hand side is where I've got the shoulder with the sharp fillet, right? So that one's gonna be a KT of 2.5, yep. .5. Okay, so what we have here now is we have all of our conditions identified for left and right sides of each one of these, okay? And the reason we need left and right sides, because we're noticing they're not always the same, left and right, especially when it's KT factors. So we need to determine the minimum shaft diameter for both the left and the right-hand sides. And then we're going to pick the larger of the two to be the actual minimum. So there'll be 2 calculations for B, 2 calculations for C, 1 for A, 1 for D. Okay, just because of the nature of beginning and ending of our shaft. All right. Okay. Now, I also want to kind of remind us when we did our keys, right? When we did our keys, remember how I said you have to keep your key within the confines of the hub, or in this case, the width of the gear. Okay. The reason for that is when I pick the appropriate KT factor, I pick the larger of the two, unless you go into another area, then you have to combine those two. So for instance, if my key here would have extended into the radius, and this as the designer is what you have to be aware of. If I extend into the radius or into that shoulder, now I no longer have a KT factor of 2. I've got a KT factor of 3.5. Does that make sense to everybody? And that's your responsibility as the designer. Okay? We're going to assume that you're a really good designer and that you're not going to interrupt anything on the outside. So we're always going to pick the larger of the 2 KT factors. So for instance, at A, we can cross out the 1.5. There's only one here for each of the left and the right-hand sides here. But up on C, we're going to cross out the smaller of the 2. And the larger one is going to be our KT factor. Does that make sense to everybody? Okay. So that's why we can't let any of those radiuses, even when if we're not using them, those radiuses for our keyways cannot extend outside beyond. Otherwise, like I said, we're going to have like really high stress concentration values. And now we have to bump our diameters up needlessly as long, and if it's something that you as a designer can control, you want to. All right. Any questions so far? This is not something the book does. They just jump into showing you, oh, we're gonna use this section of the spreadsheet, or we're gonna calculate using this one because of this, but you really never get an idea of why. At least I think so. So hopefully that's helpful. Virtual, does anybody have any questions virtually? Put the chat out. Okay. All right. Okay. So now what? Now what? Let's talk a little bit more about our conditions diagram. All right. So now what? We know that there are sections on our page 2 or sheet 2 of our Excel spreadsheet. So let's revisit that. So sheet 2, we've got shaft diameters when torque and bending are present. We've got shaft diameters when torque only is present. We've got shaft diameters when only vertical shear is present. And we've got shaft diameters when only bending is present. Okay, only bending is present. So let's go back underneath here. Now, this is the deal with shear. Shear is the one that is going to fail last. All right, we're going to find that when we have shear only, those are going to be our smallest diameters. And whenever it's in combination with something else, it like drops out. So for instance, you'll notice that at point A to the right, we have torque and shear, but we don't have a section for vertical shear only. Or I'm sorry, vertical shear and torque together. So shear drops out because it's in combination, and torque, it's gonna fail in torque first. So we designed for the torque. So this is gonna be a torque only section to the right of A. Then we've got B. Notice that shear here is in combination with moment and torque. So shear right away is going to drop out. But notice that we have both bending moment and torque at the same time. So this is going to be on both sides. We're going to use that top portion of our sheet 2 on the spreadsheet. At C, the left-hand side, shear drops out, and we are going to be a torque and bending moment on the left-hand side. And then notice that shear is in combination with moment, shear goes away, and we're going to be a moment only on the right-hand side of C. And then lastly, shear is all by itself. So now shear gets a spot. Poor shear. It loses when it's in combination, but then it's fine. We do it at the very end. Okay. So now this is how we pick. That's exactly how we pick which section of the spreadsheet. So shear, if it's in combination with anything, it loses. It just gets crossed out, and then whatever's left over is how we choose. Okay. So now we know that our right-hand side of A is going to be a torque only. Our B, both left and right, are going to be moment and torque. Our left-hand side of C is going to be torque and moment together. And then the right-hand side is going to be moment only of C. And then the left-hand side of D is going to be shear. Okay. Now it becomes easy, honestly. Now it becomes easy. But, and I'm not going to say this is a great idea, but without this, you would be trying to figure out like, okay, now where am I going to go on my spreadsheet? So this is a really important step. The book does not do it, but you are required to submit this with your work. Okay. It's an essential step, I think, before we go to our spreadsheet. Okay. So let's look at our process here. We now just got done sketching our shear and moment, or our conditions diagram. I'm sorry. So our last step, number 12, is now going to sheet 2 and using the information from the conditions diagram and the other information from the shear and moment diagrams to get the numbers, we're going to now put the information into there. So this is a good place. I don't want to make this video too long. It's long enough. I'm going to just stop the recording at this point, and then we'll start a new recording when we get into the minimum shaft diameter.